This video is going to cover multiple decrements from competing risks in contingencies in actuarial mathematics. Now, the first video on competing risks covered multiple state models and introduced us to the concept of competing risks, and then we covered some expected present value calculations using intuition to try and answer the questions where the contract is worded in a very specific way. Now we are going to move on to multiple decrement models. So there's a slight difference. Now, multiple decrement models these have one active state and they have one or more absorbing states or exit states, or absorbing exit states. Okay, now consider the standard healthy, sick, dead model, HSD model, where it looks something like this, where from healthy we can move to dead or we can move to sick. From sick we can move back to healthy or we can move to the dead state, and once we're in the dead state we can't move anywhere. Now consider under this model for the risks, consider that the policy holder will receive a payment, a once-off payment, either when they go from healthy to sick or when they go from healthy to dead. In this case, we can actually reduce this model to this. Okay, and the reason is because when we're doing pricing under this particular scenario, and where the payment is, there's only one payment and it's either on this event or on this event, then we don't actually need to take into account that line there where the life recovers, because the first time that he moves from healthy to sick, the payment will happen and the contract will end. So we don't consider that movement back from the sick state to the healthy state. And likewise, once this person moves from healthy to sick, we're also not going to pay them once they move from sick to dead, because the only payments that will be made is on H to S or H to D and on the first occurrence of those. Okay, and so this we will call a multiple decrement model, because there is one active state, and the active state here is H, and then there are one or more absorbing exit states, those being sick and dead. Okay, so this is not really a multiple decrement model, because the active state could theoretically be S or H. We actually need a little bit more detail in order to trim down that model into a multiple decrement model where there's only one active state. Okay, now multiple decrement probabilities. So what do we mean by these? Well, T AQ XR, this is the dependent probability that an individual aged X in the active state will be removed. This wording is really important. Will be removed from that state between ages X and X plus T by the decrement R. Okay, so this is the probability that, for example, if we used this R here to be an S there, where it's the person becoming sick and the decrement is sickness, then it's the probability that when this person leaves the healthy state, it will be to the sick state, and that will be between time X and time T. Okay, so the probability that a person that's now aged X in this active state will be removed from that state by the decrement of sickness, okay, between the ages X and X plus T. Okay, now it's different from something like this. This means that the life must be in the sick state at time t, given that they are now in the healthy state. Okay, this is different because in this particular case, I don't actually care what happens afterwards. All I care is that between ages X and X plus T, the life is removed from the healthy state by sickness. Here, the person can become sick, they can become healthy again, they become sick again, they can stay in the sickness state all the way up until X plus T. It doesn't really matter as long as at age X plus T, they're in the sick state. Now, it also differs because this particular person could go to the sick state and then could potentially die, okay? But that's not what we're interested in. We're just interested in the fact that they were removed from the healthy state by the decrement of sickness. Here, in this scenario, they could be removed from the healthy state by sickness or not. So they could stay in the healthy state and right at the end be removed in sickness. All that matters is that at time t, at age X plus T, they're in the sick state. Here, they don't have to be in the sick state at age X plus T. Here, they could be in the sick state, they could be in the healthy state, or they could be in the dead state, or whatever other states exist, as long as the first time that they were removed was by the decrement of sickness, and that they actually were removed by that decrement between the ages of X plus T. Okay, that's what's important to us. So there's a subtle difference between these two, but nonetheless, a very important difference. Another probability that's important to us is AP, this TAPX, okay? And this is the dependent probability that an individual aged X in the active state will still be in the active state at age X plus T. Okay, so using a very similar logic, TAPX does not equal to, assuming that H is our healthy state, does not equal to that. Okay, why? Because this assumes that the person never left the state. This assumes that the person was in the active state all the while between age X and X plus T. However, it does equal to the holding probability. Okay, now it equals to the holding probability because the holding probability assumes that the person hasn't left, will never leave. They're in the state at age X plus T, but they were also in the state between all the ages between X and X plus T. Okay, so this does hold, but they are still essentially not the same thing. So this is a dependent probability, and this here is just the holding probability. Okay, so there's a subtle difference, and that's just the way that we arrive at them. So here, the reason why we talk about dependent probabilities is because we are assuming that there are multiple decrements that are acting on the life. Okay, but here they don't necessarily have to be multiple decrements. This is just a holding probability, but it does turn out that they are equal. Okay, but there is the subtle difference between them in terms of just definition. One is a dependent probability, another one is a holding probability. Okay, now AQ XS, this is the dependent probability that the life aged X will be removed from the active state by the decrement of sickness within the next year, because there's an implicit 1 that's not written there. Okay, that's that probability. This equals to 1px_hs under certain conditions, and I'll explain that. And likewise with this, as well as so in general these do not equal each other, but they do when okay, so this is true for the HSD multiple decrement model, which is this here, but it's not true for our standard HSD model, which is this diagram over here. Okay, so let's actually explore this concept a little bit further with why some of these are equal and why they're not equal, and which the relative sizes of them. Okay, so let's use this model here, HSD. Okay, now let's compare AQXS to 1px_hs. Okay, so given that this is our model, okay, our model for the decrements. Okay, now try and fill in the relevant inequality or equality sign here. Is it that? Is it that? Or are they equal? And try and logic them out. Okay, so pause the video and try to do that, and I'm going to explain it now. So the actual answer is that this dependent probability is greater than this. Now, why is that so? Well, let's understand. This dependent probability represents the probability that the life aged X, yes, will be removed from the active state H by this decrement, okay, by the decrement that they become sick. Okay, this represents the probability that they will be in the sick state at age X plus 1, okay. Now, the reason why this is larger is because once this person moves from healthy to sick, okay, which they'll have to do in both of these, in here, they have to stay in the healthy state. But in here, they could either be in the healthy state, or they could then further on move from the sick state to the dead state. So there are a greater number of possibilities in this probability than there are in this probability. And so this probability is greater. Okay, so this probability includes the possibility of him being of the life being in the sick state, but it's not limited to that. They could also die before they're aged X plus 1, okay, which is why this probability is bigger. Now, compare these two. Use a similar type of logic and compare these two. This is the, okay, so pause it, obviously give it a try and I'll go through the understanding. So this is the dependent probability that the life now aged X will be removed from the active state within the next year by the decrement of death. This is the probability that the person will be dead at the end of the year. Okay, now, so give it some careful thought, because the answer here is actually that there. Okay, so this probability is greater. Why? Why is this probability greater? Well, this is the event that at age X plus 1, the person is dead. Okay, that's what's going on there. This is the event that between age X and X plus 1, the person moves from healthy to dead directly. Okay, not through S. Okay, so this includes a greater number of possibilities, because do you not see that in this probability the person can arrive there by going directly from healthy to dead, which is what happened here, or they can go from healthy to sick to dead. So there are more possibilities for the person to arrive at the dead state, and so this probability is greater. Now, one last one, compare these two. Okay, so give that a try. Now, understanding this is the probability, the dependent probability that the life aged X will remain in the active state between ages X and X plus 1. This is the probability that the life will be in the active state at age X plus 1, given that they are now in the active state. Well, these must be equal. And why is that? Because the life can't ever recover from being sick in this particular model. There is no arrow going back in that direction. And obviously a life can't recover from being dead. So they must be equal, because this is the probability that the life is still in the healthy state. And this is the probability that the life is in the healthy state. But the difference between this and the holding probability, which equals this, is essentially nothing in this particular case, because the holding probability is the probability that the life is still in that state, because he couldn't have ever left. Okay. Now, just to clearly define this difference, for HSD, tell me, for this particular model, the standard HSD model, we know that APX is equal to 1px HH. Now compare that to this probability, which is not the holding probability, not the dependent probability. It's the independent probability. Now, what this is, that's the inequality sign that we should be using. And the reason for it is because the person can go from the healthy state to the sick state, and then they can come back to the healthy state. But here, they had to have stayed. Okay, so there are less possibilities for the life, for the event in this probability than there are for this one. And so these probabilities are smaller than this probability. Okay, now an important thing to note is that APX plus AQXS, death by sickness, plus AQXD should equal to 1, okay, in the HSD model. Now, in the HSD multiple decrement model. Now, please note that you don't necessarily have to only be dealing with HSD models. You could be dealing with models where you're looking at employees, and you want to know how long they're going to be working at your company. So in the active state then wouldn't be healthy, it would be working at the company. And then the person can leave the company by death, they could leave the company by retirement, they could leave the company by finding a new job. It doesn't necessarily matter. So the point is that there are multiple different, or many different cases for these competing risk, the application of competing risks and multiple decrement models. It's not just strictly HSD models, which I've been focusing on so far. Okay, so this is true where the dependent probability of staying in the active state equals to, or plus, all the dependent probabilities of leaving by all the different decrements. That must equal to 1. And why is that the case? Because at the end of this particular time period that we're concerned with, the life would have either stayed or would have left to one of the other states. So that must account for everything, which is why they sum to 1. Now, the sum of all the dependent probabilities of leaving the active state, this we can simplify into just that and omit the superscript on the right hand side. Okay, which obviously means then again that APX, the dependent probability of staying in the state, plus the dependent probability of leaving, equals 1 again, okay? Because you either leave or you stay. Now, we said that T APX was equal to TPX HH. And this equals to the exponent from negative, the integral 0 to t, sum j not equal to h mu x plus s. Okay, so these are all things that we've covered up to date. I'm just putting it into this format here so that you actually recognize that this and this are related, and they're related through this holding probability. Okay, now in the HSD model that looks like this, so the multiple decrement HSD model, we have that T APX equals to e to the negative mu plus sigma t. Okay, so all that I've done here is I've replaced the summation with all the different forces of decrement, okay, which is mu, which would sit here, and sigma, which sits there. Okay, and this is assuming that there are constant transition intensities. So when I then take that integral, I just get out the same two constants, okay, when I'm integrating between 0 and t. Okay, now if they weren't constants, I would have just left that as an integral. Okay, now we have things that are called Kolmogorov's forward differential equations, and these are these two equations in this particular model. Okay, and then the solutions to these differential equations is as such. T, this is really important. Okay, so then obviously generally when t equals 1, so we're just dealing with the 1-year dependent probabilities, then we just sub in the 1 for that t over there. And then also note that this is for constant transition intensities. Okay, so these formulae are very important because if you have to calculate dependent probabilities, you have to work with these transition intensities. Okay, and likewise, if you have to calculate transition intensities given the dependent things, you're going to need to know this formula as well, or I'm going to get to it, but the inverse of the formula where you solve for sigma or mu. Okay, now under single decrement models, TQXR, this is the independent probability that an individual aged X in the active state will be removed from that state between ages x and x plus t by decrement r. Now you might say to me, George, that's the exact same as what we had before. It's not the exact same. The difference is I've changed dependent to independent. Okay, so what I mean by that is previously when I wrote it as the dependent probability for these types of dependent probabilities, I'm saying that there are multiple decrements acting on the life. Here, even if there are multiple decrements acting on the life, and I need to calculate the independent probability, I must assume that there's only one decrement acting on the life, and that is this decrement R. That's the difference between this and this. This assumes that there are other decrements acting on the life. This assumes that there is only one decrement, and that is the decrement R that is acting on the life. Okay. So, when we set mu equal to 0 in these above equations, what we should get is this independent probability. Okay. In this equation here, if we set mu equal to 0, what do you notice happens? When mu equals to 0 here, what we get is sigma over sigma, which cancel out, and then we're left with 1 minus e to the negative mu t. Okay? And this is exactly what we previously know that to be. Okay? From all our previous chapters, because TPX was equal to e to the negative mu x. So this is 1 minus TPX when this is an independent probability, and thus it's the only probability, it's the only decrement that's acting on the life. And I know that this plus this equals 1, and so this must be true. Okay, but this is true when mu, okay, so I should have done this over here. And then I should have said when sigma equals 0. Okay, so I'm sure that wouldn't have affected the understanding, but if you were confused, that's the difference there. Okay, so in this case, if now mu equals 0, then this would have been 1 minus e to the negative sigma t. Okay, so that's the difference there. Okay, but let's remove that so we don't confuse ourselves. These are still our dependent probabilities, and this right here is our independent probability. Okay, now let's move on to multiple decrement tables. Okay, so AL X is going to be the active population at age X. So similarly to how we have LX being the number of people that are alive at age X, here we're talking the number of the active population at age X. Okay, then AL X plus 1 should be equal to ALX minus the number of lives removed between X and X plus 1 by all the decrements. Okay, and this here is equal to ADX, okay, where I haven't specified that superscript. Now, if I specify the superscript to be, let's say, R, then this is the number of lives that were removed from the active state when they were aged X by the decrement R. Okay. So that should be simple enough. Now, we know that AQ XR is equal to AD XR over ALX. Okay, so the total number of the active population at age X we divide the number of lives that were removed from the active population by decrement R by the active population at age X to get the dependent probability that the life is removed by the specific decrement R at age X. Okay. Then APX is equal to AL x plus 1 over ALX. Okay, and then N APX is just going to be equal to AL x plus N over ALX, and then we have AQ. Just bear with me for all these formulae, just something that we have to do. Let's actually write one more. Okay, so this is the probability that between ages X plus N, the life will be removed from the active state by the decrement R, and that will equal to the total number that were removed between the ages of X plus N. So while they were aged X, while they were aged X plus 1, X plus 2, X plus 3, all the way up to age X plus N minus 1. Okay, so before N periods is up, removed by the decrement R from this initial population that were alive and in the active state at age X. Okay. Now, this deferred probability will equal to will equal to that, because the person must survive until age X plus N, or must stay in the active state until age X plus N, and then at the beginning of the year they are in that active state at age X plus N, but then before the end of that year they must die, which is this, and so the two AL X plus N's cancel. Okay. Now we define A mu xk to be the force of decrement or the transition intensity due to k at age X. Okay, so due to the decrement k at age X. So this is our force of decrement, or our transition intensity. And now you might say to me, but previously you haven't been writing it like this, you've been writing it as such. You've been writing mu x k. Okay, well the reason why is because this actually equals to, it actually equals to that there for all decrements k and for all ages of x. Okay, and this result here is what we call the independence of decrements. Okay, that's what we call the independence of decrements. And now the reason why this is so, the intuitive understanding of this, is because in an infinitesimally small time interval, there's only enough time for one of the decrements to take place. And so the independent transition intensity is no different from the dependent transition intensity, because at that particular point in time, the life can be removed from the active state by only one of them. There's only enough time for them to be removed by one of them. And so we're assuming that those two forces are exactly the same. And that's not the same for our dependent and independent probabilities of decrement, but it is the same for our independent and dependent forces of decrement. Okay, they are the same thing, or they at least equal. Now, if you want to construct a multiple decrement table, you need all of these formulae for the multiple decrement tables here, and then you can go ahead and use all the different results here to calculate the next thing in the table, or to work backwards to calculate the previous thing. And typically the results that you'll be needing is a variant of this result, where just remanipulation, which makes sense to us. It's that the number of people that are removed by the decrement R should be the total number of people that are in the active state times by the probability of being removed by that decrement. So that makes sense to us. And then you also use this formula here to go ahead and calculate the ALX plus 1 in the next year. So if you want to calculate a multiple decrement table, which is basically a table of the ALX's and the ADX's, then you go ahead and you use that formula and that formula there to go ahead and move through the different things. And then you might also need to use these formulae for the probabilities if you were given the forces of decrement. Okay. Now, if you want to find the forces of decrement from an existing multiple decrement table, then we will do this. So AQ XS is equal to sigma over mu plus sigma. And this is multiplied by that there. Okay, now what do we notice about what's inside this bracket? Well, this here is the formula for APX. Okay, so we can substitute that in there. APX. Okay, well, what do you notice here? 1 minus APX, well, that equals to AQX. Okay, now we must try and manipulate these two in order to just be left with sigma. Okay, so if I leave sigma on this side and I take the mu plus sigma and this AQX to the other side, then I have sigma is equal to AQXS, this one here. I divide by this on both sides, and then I multiply by mu plus sigma on both sides. Okay, and I arrive at that. But now, where do I also recognize this mu plus sigma from? Well, in e to the minus mu plus sigma, this was equal to APX. Okay, but I just need the mu plus sigma there. So I take the natural log of both sides, and then I'm left with minus mu plus sigma equals to ln of APX, and then I multiply both of those by the negative, and I get that. Okay, so then I can substitute that in for this mu plus sigma. That negative goes there, and I get ln of APX. Okay, so here is my formula for sigma, and you can follow similar logic to get the formula for mu. Okay. Now, a useful tip is to always go ahead and find the underlying forces of decrement in order to go and find the dependent or independent probability. So if the question asks you to go and find independent probabilities or dependent probabilities given the other one, the link is the forces of decrement, and the reason is because of the independence of decrements, these two being equal. And we know the formulae for both the independent and the dependent probabilities in terms of our forces of decrement. And so forces of decrement are the link. We can go and calculate them with the forces of decrement. Okay, now the relationship between our independent and our dependent probabilities is as follows. So TAPX is equal to the exponent of negative integral 0 to t, the sum a mu x plus s j ds, okay, where, so I'm just going to use here j equals 1 until n, and I'm going to assume that that covers all the possible decrements. So j1, j2, 3, 4, 5, those are all the different decrements, and then we have n different decrements. So when I take this sum out here, I can take the sum out of this integral, and what that means is I have, instead of an integral of sums, I have a sum of integrals. And a sum in an exponent is the same as, so in other words, e to the a plus b is equal to e to the a times by e to the b. So the exponent of a sum is equal to the product of exponents. Okay, now what that means is I can take this to be the product from j equals 1 to n of the exponent negative integral 0 to t a mu x plus s ds with the j up there still. Okay. Now, because my dependent and my independent forces of decrement are the same, I can actually just write this as such. Okay, so all I've done is I changed that dependent force of decrement into an independent force of decrement. But what do you notice? What is this here? This here is just equal to TPX j. Okay, so now the probability of staying in the active state from age x to age t is the probability, is the product of all the independent probabilities of not leaving. Okay, so in other words, this is TPX, let's say d, where the decrement is of death. This here is the same thing as the probability that a life aged x will still be alive at age x plus t. Or if you did r there for retire, then this would be the probability that the life aged x is still employed at age x plus t. So in other words, they haven't been removed by the decrement r. And if they could have been removed not just by retirement but also by death from the active state of employment, then I would have had that d there. And those two probabilities, the probabilities of staying in the active state, in this particular example of employment, the product of those probabilities is just equal to the probability of the person staying in employment. Okay, not leaving due to any decrement is equal to the product of the independent probabilities of not leaving the particular active state. Okay. Alright, now the last thing for this video is integral formulae for multiple decrement models. So this is only useful if our transition intensities are not constant over a year of age. So if they're not constant over a year of age, then our Kolmogorov forward differential equations become this. Well, they don't become this, they stay the same. Only difference is now I'm writing x plus t here because I'm not using a constant force of decrement. I'm not using a constant transition intensity. I'm allowing it to vary as time progresses or for different ages. Okay, so this is just obviously the same thing as t a p x, and just rewriting this instead of it being in its independent decrement form, being in its dependent decrement form, we have a mu x plus t s. Okay, and then solving this particular thing, this particular differential equation, gives us aq x integral from 0 to t now, let's say to t there, maybe I shouldn't use s because I'm using s as my decrement, so let's change this variable to let's use r. Okay, then this equals to integral from 0 to t Okay, so once again we have just swapped the dependent transition intensity for the independent transition intensity, but otherwise they're the same. Okay, so if I have transition intensities that are not constant over a year of age, then I have to leave it in this integral format here. And that the way that I get to this integral is I just integrate both sides of the equation from 0 to t. Okay, and then obviously I have to change this placeholder variable from t to r here because I can't integrate in terms of the same variable that's in one of my bounds. Okay, so if we don't have a constant transition intensity, we have to leave it in this integral form in order to calculate this. So that's the relationship then. All right, so if you have any questions regarding multiple decrements, regarding competing risks, leave it in the comments down below. I'll try and tend to them. And other than that, in the next video, I'll be moving on to the unit-linked contracts with profit contracts. I'll do profit testing, all those different things, unit fund accounts, unitized with everything. I'll be moving on to that type of thing in the next video, and hopefully I can try and do that in one short video. I know it's a slightly more complicated section, so I don't want to go through all the particular nuanced theory, which will probably not benefit you that much, or rather would not benefit you as much as just reading your textbook or your prescribed text. But I want to go through an example to show you how it all actually comes together in practice. Okay, so I'll do that in the next video, and I'll see you in that one.